oh, sorry, an RL circuit. So I guess a DC RL circuit. We'll do the same type, similar setup. Make that more obvious. I have some inductance L there, I have some resistance R. We'll throw the switch on. So I'm going to have current flowing through this thing, and then I'm going to break the circuit. So I'm going to connect it, get current flowing through, I'm going to break it. Now, if the inductor were not there, then as soon as I break the circuit, current stops everywhere. But because of the inductance, because I've got a second, suddenly because I have the inductor into it, it's going to slow the collapse of the current. Because as I break this, the current flowing through here is going to start dropping off. The inductor goes not on my watch as best I can, and so it's going to create a current that tries to bolster it up. And perhaps you'll be sad to know that there will not be a second order differential equation here. I'm sorry. So once I break the connection, this whole part over here becomes irrelevant, and I'm just left with my inductor and my resistor. It's not going to go on forever, but it's not an instantaneous drop. So let's see, I got current flowing around like that. So what I'm going to do is, well, voltage across the resistor plus the voltage across the inductor would be equal to 0. Make sure I hit my minus signs in the right spot. If I have current that is flowing across here, that's not going to be going that way. I'm going to lose going across my resistor, so it's going to be whatever the current is times the resistance, and then I'm going to lose going across the inductor, negative L di equals 0. I have a first order differential equation. And how do you solve it? Oh, I do want to point out, unlike before, whatever current is flowing across the resistor also has to flow across that. It's not like, we're not storing charge anywhere like we were over there. All right, so how do you solve it? This would be a Calc 1 problem.
Are you asking like what the variable?
I'm asking, how would you solve it? What's the first step?
Putting the current resistor on the other side of 0.
Moving one of those from one side to the other? Okay. Negative IR equals L di dt.
You're gonna divide both sides by L and integrate.
One other step before that. Or two, depending on how you want to break it down. If I integrate, I'm going to run into issue because I have current over here and current over there.
Yeah.
I need to get my currents together
Oh, divide by I.
and multiply by dt. So I get negative R over L dt is equal to di over I. Now we agree. So I have negative R over L t plus some constant equals natural log of I. So I to e to the negative r over L t plus c. That c is constant, that's not capacitance, which equals e to the c times e to the negative r over L t. So when time is 0, so time is equal to 0, my current is equal to e to the c. So this is just whatever my initial current is. So the current that's flowing through when I disconnect, and so my current now can be described by whatever my initial current is, e to the negative r over L times time. In other words, if we look at that plot of current versus time, we start out with some maximum amount and then it decays. If we make a small adjustment to that, we have a current as a function of time is equal to my initial amount, e to the negative t over L over R. The reason I put it in that form is that if I can get this equation into negative t over tau, this tau here is known as the time constant. And it gives a measure of how long it takes to decay. When t equals tau, my current will be I sub naught times e, so at t equal to tau, equal to the negative 1. And so if you calculate that, you can, for some reason I'm thinking it's 67%. I'll just be making that up. What is e to the negative 1?
What the actual number? 0.36.
0.36? No. It's a 0.365. So you lose 60, that's where the 60 something came into my head. So you've lost 64% of your current at the time constant t, tau. And so for an RL circuit, the time constant would be L over R. The bigger that ratio is, the longer it's going to take. And it makes some sense that if R gets smaller, I'm going to get a bigger time constant, so it's less resistance, I'm going to lose less. Questions to hear?
So, can you explain the difference between RL and LC again, like what that exactly means?
It's a reference there, the shorthand notation, if you see RL circuit, first off, backing up, there's DC and AC. The direct current always flows in the same direction. And then alternating current, where deliberately currents alternating directions. And then another way of identifying circuits is by the components in it. So an RL circuit would be a circuit with a resistor and an inductor in it.
But it could be an AC or a DC.
Yes.
Okay.
Yeah. We potentially could be more specific here. This is an RL parallel circuit, as opposed to RL series circuit, which would be that.
And if it has a capacitor in it too, would it be an RLC circuit?
Yes.
Okay.
Yeah. They really stretched their imaginations when they were coming up with that name.
And then what is the point of the little gates that you put in there? Like, would they open or close?
The purpose of the gate is I have to have some current flowing.
Yeah.
And when I do my analysis, I didn't want this involved. So I got current flowing and then I broke the connection.
Cause you only wanted to look at the components? and
Yeah.
What they're doing?
Yeah.
Okay.
And the fact that, I mean,
So
I think
you
it makes
start
sense.
you start the current flowing and then break it before you get, like, just so you can have the current for your calculations basically, but break it so you don't have to include the rest of the circuit?
Right.
Okay.
Yep. It's a simple circuit and something that we can easily reproduce on the board.
Is this what we'll be doing in the lab with where we're switching off the circuits?
No, in the lab, you'll have basically, two solenoids, one inside the other. You're gonna run current through, like we run current through the inner one, and then shut that off. And as that current collapses, it's gonna change the magnetic field inside the larger one, which should induce a current in the larger one. That's the lab we're gonna be doing.
And then we'll look for the current in,
Yeah.
in the large one.
And so then you'll try to figure out how, you should be able to measure the current coming off that is going to change there and compare that to sort of what you would expect, theoretical. And I'll just tell you now, when I first did the electromagnetic induction lab, got really excited. I was conducting it before I wrote it up, got really great results. And I thought, oh man, great. You know, so many physics labs, the results are just so bad. It's nice to get one that's gonna work out well. So I wrote it up, handed it out, they did it, and they were getting like 10,000% error. No, it worked out. So and it was consistently, you know, huge error across the board. And I was thinking, how did I get such good results? And what I think I did was I basically had some value, and then I used that value later on to derive itself, and I basically did a little circular logic, so I got great results. So that was the start of my electromagnetic lab and electromagnetic induction lab. You know, after a couple of years, I got tired of 10,000% errors, and so I revamped it. So now, when you get errors under 100%, I'm thinking victory. So they might seem bad to you, but that's only because you didn't do the really bad lab. We have 4 minutes. Okay, questions? All right, let's talk about where Kirchhoff breaks down. Or not. That was the not talk about it, it was the not breakdown. We need to somehow account for something. Kirchhoff said that in a junction, whatever current flows in flows out. So if I take a simple capacitor circuit, a DC C circuit, I have current flowing onto here, so current flows onto here and it flows off there, or negative charges flow onto the right plate, negative charges flow off the left plate. Whatever current flows onto the capacitor flows off the capacitor. Then in that sense, Kirchhoff still works. However, we do have a gap there. We are building up charge. So we've got this issue here of whatever current's flowing onto that plate doesn't flow off of that plate. So in that sense, Kirchhoff's rules don't seem to work, because I have a point in the wire where it flows on but doesn't flow off. It flows off over here again, but not more immediately.
This is assuming an actual gap, or like you have a insulator in there?
Well, even if there's an insulator, their charges are going to be going through it.
I was just curious. So it doesn't matter.
Doesn't matter. So we need to somehow address that. I know that the reason why I paused there is I get minus lines in the wrong spot, which I just find frustrating to do it. Alright, so I have some charge here, Q. And I'll charge negative Q there. So let's take a look at this plate. I know that the electric field between the plates is equal to sigma over epsilon naught. We'll just assume for the sake of this that there's no insulator in between. And that's the charge density Q over A epsilon sum naught. Now I know Q is changing, because charge is still building up here. Let's assume we're not at max capacity, but I have charge that's building up on it. So I know that Q is equal to epsilon sum naught A times the magnitude of my electric field. dq dt is equal to epsilon sum naught A dE dt. So since I have charge that's building up on the plate, I mean, once it's at maximum capacity, there's no more charge flowing on. I wouldn't expect any charge to flow off. But I do have charge flowing onto the plate, so there. And this area here is the area of, well, in essence, the area of my Gaussian surface. But that's going to be equal to, I'm going to throw that A into my differential. And what is the area times my electric field? Flashback to, what, a month and a half ago?
Lots is law.
Yeah.
What is it?
So we have, I heard flux.
Oh, yeah, that was.
This is a pseudo derivation, it's not the painstaking one. So I seem to have this change in charge with respect to time, in other words, a current, is equal to this. Now, this is not the traditional current. The traditional current is I have a charge actually moving here, but as I have charge flowing onto the plate, I have this flowing off, sort of the symbol for what's flowing off the plate. This is known as the displacement current. So if we add this to Ampere's law, E dot dl, which is mu naught I. If we change this I, and we tack on this, we have the regular current plus the displacement current. So this is mu naught I plus mu naught times epsilon sub naught d phi E dt. Mu naught. This is what Maxwell contributed. Well, this was the cornerstone, and then the rest of what he does is what made him famous. So Ampere's law with Maxwell's correction, or Ampere-Maxwell's law, however you want to word it. But with this, we now have some implications that will revolutionize physics. But that is going to have to wait until Thursday.
So what you were getting at there is that the charge is not going to go across that gap,
Right.
but that helps us describe it anyway.
Yes.
Okay.
It is a They labeled it a current, just to keep the law, or Kirchhoff's rules valid. Traditionally, it's called a displacement current.
What if you have a semiconductor in there? So then it acts as a capacitor and, something that transfers the charge, right?
I thought it acted as a huge resistor or a conductor,
Yeah.
so it doesn't.
Isn't a resistor like, insulator too? And can't an insulator act as a resistor?
It can,
Yeah.
it can. Well, if it's called an insulator, then it's probably high resistance.
But it theoretically, a semiconductor should have less resistance, and even less depending on the conditions, right?
Alright, so semiconductor is, if you have enough energy, it will act like a conductor. If you're below that threshold, then it acts as an insulator. So if there's not enough energy, then you won't have, semiconductor doesn't build up current until it goes over the dam and comes flowing over the wall.
Can you use it as an insulator in some cases, and then like, if you build up the energy or whatever, you can become a conductor or something?
Yeah, but you would have to build it up in a capacitor, I think, or something like that. I'm gonna have to read a little bit more on semiconductors.
I came across it in the book, we were talking about semiconductors for a little bit, chapter 28. Just got me thinking about it.
Typically don't do the semiconductors, so, yeah, I have to read up again. I can't do that cold.
Is one of those little gates that you use in your circuit, can that be like a logic gate? You think of it as that? I learned about logic gates in different class.
Because when I picture logic gates, I'm picturing
It's either going.
and or.
Yeah, that thing. It's either becoming a 1 or a 0 based on a high or a low current or whatever.
I view those as different, because that's,
Or I guess it's higher or low voltage.
because that doesn't stop current, that just identifies the value.
Oh, okay. I guess it could theoretically be 0 current though.